Hey guys, what's up? It's me Rahul Saxena, your Udacity's mentor, welcoming you all to the first webinar of our nano degree. It's great to see that most of you have completed the first project. Now it's quite clear that you guys are clear with the concepts related to backpropagation and the architecture of neural networks. If you have any issues related to the first part of project, you can schedule a video call or message me via Udacity's chat box. We can definitely discuss and sort it out as soon as possible. So I can see that almost all of you are online. Hi Josh, hi Matt, Selena, Alina, Daniel, Yuya, Lauren, Ram, Andy, Rohan, hi Seb, hi Annie, hi Andrew, hi Mary, hi. Oh dear. So perfect. So all 15 of you are online. Now we can move to the webinar related to the convolution neural networks. I'll be discussing about the convolution neural networks. It's one step ahead of the normal neural networks. These were mainly invented to solve the computer vision problems. Okay, in the early days, the everything used to be manual, so it doesn't scale well in that case. That's why these were invented. Okay, so I'll be switching to my slides. If you guys face any kind of difficulty in between, you guys have any questions, you can use the chat option and ask me. I'll try to get it answered by the end of the webinar. Okay, perfect. Let's switch to my slides. Okay, I hope you guys are able to see my screen. If you're facing any issues, please let me know in the comments. In this webinar, we'll discuss the basic working of convolution neural networks, the different types of layers that are generally used to build a convolution, some of the applications, and some popular architectures. Let's start with the introduction part. So what are the convolution neural networks? Convolution neural networks are basically a class of deep feed forward neural networks. They they were introduced mainly for solving computer vision problems. Computer vision problems like object recognition, object detection, self-driving cars, all these things, they are dependent on convolution neural networks. Now let's talk about who introduced these type of networks. In 1995, Yoshua Bengio and Professor Ion Lucan, these legendary guys, they introduced this convolution neural networks. You guys might have heard of MNIST handwritten images recognition data set that was also curated by Professor Ion Lucan. Okay, now convolution neural networks expects inputs as images. As I mentioned, inputs, they were mainly introduced for images, for solving the problems related to images. So it expects an input as an image. They make feed forward function more efficient to implement. The colored images that we capture consists of RGB channel. So if we have a color image of 28 by 28 pixels, then we will consider the input to our CNN a matrix with width as 28 and height as 28, and depth will be 3 because there are three channels R, G and B. Okay, so the depth will be 3. Now the question might comes to our mind, that why do we actually need a convolution neural networks? Why we need convolution layers when we already have fully connected layers with us? Why do we need these? Convolution neural networks, these are specialized type of neural networks. They are the fully connected structure of neural network does not scale for large images. In case of large images, the parameters increases to a lot exponentially. So let's say we have two images. We have images of 32 by 32. uh, the width and height of images are 32 by 32, and 3 is the channel size, and we are converting that image to using a convolution layer to a 28 by 28 into 6 channels image, 6 channels matrix. Then if you multiply these matrix the dimensions, then you'll be getting more than 10 million parameters. That's gonna consume a lot of memory, so that can be actually expensive, and in that case it's going to be kind of overfitting problem. So due to this reason we use convolution layers, because the images, as I have written, the images are high dimensional vectors. The number of parameters increases exponentially, but in case of convolution layers, you may notice that it only needs 150 200 parameters for the same problem. So this is gonna save a memory and as well as the training time, and we are going to get better, much better results than a normal neural network. Okay, the second most important reason is parameter sharing. What is parameter sharing in convolution neural layers? We use filters to scan over the image, so those filters move over to say different images, and it generally builds a feature. These are kind of feature detectors, so it the same feature detector, when it moves to different images, so it builds a kind of pattern uh, that helps to predict or understand the hidden patterns of the dataset. Okay, now let's discuss how they actually work, how the convolution neural network works and processes our images. So basically, they cannot, as you know, convolution neural networks at core are neural networks, so they cannot understand images as we humans can do. We use images, we'll have to use the image pixel values to feed the neural network. Each pixel intensity of RGB, red, green, blue channels gets expressed by a number, that is the pixels value. Okay, so this way we feed our data. The pixel values are fed into the layers. Now the scanning of image. This is the main part. How scanning works. The scanning, the convolution layer focuses on a set of pixels. It considers a square patch, or we can say filter, and passes it or moves it through the image. I'll show you the whole thing in the next slide. Okay. Yeah, the filters, as you can see, here are the filters. With the mouse, yeah. So this is kind of patch. It moves through the image and builds a final result as a filter. And the movement of patch, the we move the filters across the image step by step. When we move it step by step, the size of each step is known as stride. Let me show you an example by the enriched carpathy. Yeah, here as you can see, the this patch is moving over the image and giving us some output volume. These are the values. So these are the filter weights. It gets multiplied with the input image and gets gives it the as the final values, final output. So this way we can actually use it. So now we are aware of the basic working of our neural network. Let's move on to the types of layer that helps us to build a complete neural convolution neural network. Because the thing that we discussed, it's about convolution layers, how convolution layers work. So as you can see this sample architecture, I have grabbed this image from the Stanford's CS231A course. If we input an image of a car and passes it through a convolution layer with an activation that is ReLU. ReLU is a rectified linear unit activation function. You can go through the notes in the notes that I have provided along with this video. You can check the uh, details about these activation functions. So we passes the input image through this convolution layers, then it finally helps us to build a get this kind of metrics, and then we use pooling to reduce the size of our width and height of metrics. And then after pooling layer, this is the next layer that we use. This is the next convolution layer that we use. In a similar fashion we move on, and ultimately we use we flatten the final outputs of our convolution layers, and then flatten the images. Why flattening is important? Flattening means to convert a 2D 3D matrix into a one dimensional vector. Now this vector uh, is used as input for our fully connected layer. Either we can use one fully connected layer or multiple fully connected layers, and then we pass a softmax active with the outputs through a softmax activation function. Why softmax? Softmax is used because we are trying to understand whether it is a car, it is a truck, or van, or something else kind like bicycle. So to get the probabilities of each of the class, we use a softmax activation function. So okay, so let's discuss what the convolution layers. As I said, the convolution layer applies a convolution operation to the input and passing the results over to the next layer. The convolution layer emulates the response of an individual neuron to the visual stimuli. The each layer of the convolution layer helps to learn more about the image characteristics, but using many convolution layers can lead to overfitting. So we use some regularization technique. As I said, we can use we here we are using the diagram is showing that here's the one first convolution layer, the second, and in between it might be using a couple of more convolution layers. So we can use numerous convolution layers, and that is a core thing of deep learning. Deep learning is all about using many layers of neural networks to build a, a really good algorithm, good machine learning algorithm that can help us predict great results, human like results. Okay, so but there's a problem that if we use many layers, then there comes problems of vanishing gradient and these kind of problems. For handling these kind of problems, we will have to use some regularization techniques in uh, as you know, the in the linear regression part we use a bias term for as a regularization parameter. Similarly, here we use some regularization techniques. Now let's talk about the activation layers. uh, just a second. Yeah, the activation layer, the purpose of activation layer is to add non-linearity. We won't use any activation function like a simple linear activation function that so it's gonna give us the results as a linear activation function. Sometimes it's asked that what if we don't use any non-linear activation function and just pass it through a linear, then it's gonna give us results as a linear regression, nothing else. So to add non-linearity to handle real life situation, it's important to use a non-linear activation function. We with the hidden layers, it's recommended to use leaky ReLU or ReLU activation. Leaky ReLU is a specialized type of activation function that you can that you can read about in the study notes. Okay, to predict the final probability, as I mentioned earlier, we use softmax activation to get the probability of each of the classes. There are other types of activation functions that you can read about. Here, let's like randomized leaky ReLU, parameterized leaky rectified linear unit, exponential linear units, 10H, softmax, softplus, softsign. These are kind of activation functions that we can use, but all of these has some pros and cons, so it would be great if you try to read about it. Pooling layer is for reducing the specifically for reducing the size of our the width and height of our matrices. So there generally we use either max pooling or average pooling. The max pooling, as you can see, if this is kind of 4 by 4 matrix. Here we have 4 by 4 matrix, and we will divide it to, we want to get 2 by 2 matrix out of it. So if we'll use max pooling, then it will divide in this way, like 4 sub matrices. uh, in a max pooling, it will try to get the maximum value. So 20, here we'll get 30, here we'll get 112, here it is 37. So this way we are getting 20, 30, 112 and 37 as a max pooling result layers output. Similarly, this thing happens in average pooling. We calculate average of all four values and output it to the final matrix. Okay. Dropout. What is dropout? Dropout is primarily is a very common technique that we use while training. It ignores and drop neurons, like in this kind of neural networks, as you can see, the the enormous computations that are happening over there, and this is gonna increase the memory footprint. So to reduce this, we use dropout. This helps. This works like a regularization technique, and but make sure you don't use dropout in the inferencing part. Okay. Oh, perfect. So as we discussed, first of all we'll use convolution, then max pooling, dropouts, and then finally we flatten the layer. At the time of flattening, then we proceed with a couple of fully connected layers or one fully connected layer. The final results of the convolution layers and previous layers are flattened to 1D vector. This 1D vector is then inputted to the one or more fully connected layer. So these kind of layers all we need for a neural network. So now let's move on to the application part, application and popular convolution neural networks. What are the applications? The convolution neural networks were mainly, as you know, they were mainly introduced for solving the images related problem, like image recognition, self-driving cars, text extraction for images. Uh, for example, I'd say if you have seen the Google Translate application, then it captures an image. If you see a signboard and you guys can capture an image using it, it's gonna extract images and then translate it using some other algorithm, using some other type of AI algorithm. So the way it extracts it from the image, that is that is using convolution neural networks. Self-driving cars, it detects the cars that are moving along with it on the road. That uses convolution neural networks. Face recognition, Apple's phone use face recognition. That is also based on convolution neural networks. But recently, uh, researchers have started exploring the CNNs to a different level. They have started using building voice user interfaces, like you can read about the Google's DeepMind's WaveNet model to generate realistic images using CNNs. Human-like images using CNNs. Natural language processing is also being explored. You can read about it by going through this link. Let's talk about some popular CNN architectures. There are a couple of architectures that are very popular, like Linet, LXNet, VGG, Google Linet, ResNet. So Linet was introduced by Ian LeCun, and it was, as you can see here, the LXNet was introduced in was by the Jeffrey Hinton, In 2012 ImageNet competition, it used only 8 layers. Then if we talk about VGG, it used 19 layer and was one of the winners of VGG ImageNet 14. And similarly, the Google Linux that was introduced by Google, but uh, they named it like Google Linet. So that used around 22 layers. The ImageNet in 2015 competition, Microsoft introduced the ResNet network, and it had 152 layers. That's really a great model that helped to get amazing accuracy. Here you can see the losses percentage of all the networks. So I hope this presentation might have given you some introduction about some clarity about the how convolution neural networks work. Uh, Please let me know if you have any questions. Thank you.